a closed loop of wire and I rotate it, guess what I do to the magnetic field intensity? If I'm holding my arms out like this and it's raining and the rain's coming straight down, boom, right through my arms. I got a lot of rain coming through my arms, yeah? How about I turn like that? How much rain coming through? None. Okay, how about I go like that? Some. I mean, I can't keep doing it. You see what I'm saying? But I could clip the amount of rain that I'm. You see what I? Same thing over here. In the magnetic field, you're rotating a loop. You're changing the magnetic field in that loop, honey. You get a voltage, and that voltage light up the lamp. You see that? Yeah. I mean, it's just not an interesting little gadget here. I want you to see what's going on with it, huh? Okay. Here's a piece of aluminum. Aluminum, does it have magnetic domains in it? Answer begin with the N. No, very good, okay. No magnetic domains. But watch this piece of aluminum, which is not a magnet now. Is this the first time you've seen that? Remember that. Do you know how we put things in orbit now? The way we put things in orbit is we take a rocket and we and it keeps picking up speed and finally goes into orbit. Okay? But what are we going to do in the future? Well, you can't do it with people inside, gang. But if you want to get something into orbit, okay, instead of a gradual acceleration and a pickup in speed, they'll be doing this. So today, remember today's the day you first saw that. This is a very, very serious candidate for propelling things from the Earth up into orbit. Okay, yeah, electromagnetic propulsion. Now, why did this thing fly out, gang? Should I leave that as a question for you? How many would have the next few days completely spoiled by not having that information? Why did this thing fly out? Why did this all of a sudden become a magnet? Maybe there is no reason for that. Maybe it's just one of the strange things about the world. Now, let me ask another question. Let me go like this. I held it way down here where the magnetic field was strong. Let's suppose I just put it there. Ah. Electromagnetic levitation. How come that thing is levitating? Why? This becomes a what when I plug it in? Begin with M. Magnet. And this is levitating, so this must become a... But it's aluminum. But it's a closed loop of aluminum. It's a closed loop of aluminum in a changing... Oh, I'm starting to get it, Let's see, this is a changing magnetic field because it's AC. And there's some connection between a changing magnetic field and a closed loop. You guys be getting it? No, I guess there's no connection. Or is there? How many know why this thing was levitating? Did you ever see one magnet repel another? What did you just see now? You saw one magnet repel another. And why did it fly off when it was way down here? Here's a question you can all answer. Every one of you guys can answer this. This thing weighs 1/8 of an ounce. I'm making it up. 1/8 of an ounce. What is the strength of the electromagnetic force pushing up on that ring? Check your neighbor. What's the answer, gang? 1/8 of an ounce. That's old mechanics, right? If there's 1/8 of an ounce pulling down and there's something pushing up to be keeping equilibrium, that up must equal the down, and that's a 1/8 of an ounce. Ted Bradstrom has some ideas of electromagnetic induction he wants to share with us today.
Speaking of electromagnetic induction.
He's got a nice one here. Very simple, really nice.
Magnet. Coil. So we know if we move a magnet through the coil, what's going to happen? Hopefully we get current flowing. Okay. Goes through the wire, meets another coil. What happens when you get a current through a coil? Magnet. Okay. So we put a compass in the middle of this. And, okay, let's see if we get it. There we go.
Look at that, gang. Look at that.
Okay.
An interaction from here to there. Hey.
Well, just in case you think we were lying, I'll just move this, and you can see how it's moving, right? Is the
Nothing moves down there, yeah? Now watch when he changes the magnetic field in the coil. What happened down here, gang? Yay. All right? Okay.
Do you want to know the fun part? You don't have to move the magnet. You can hold the magnet steady.
Yeah.
And move the coil back and forth.
Hey, you know what? You know what is a neat application of electromagnetic induction? It's just been the last few years, and that's the smart lights. When you're traveling down the road and you're coming to the traffic light, and the lights change for you. You drive over something, and that something changes the lights. They used to put like a piece of rubber tubing out there with compressed air, and it would, boom, make a little pulse of air, and that changed the light, but then the rubber would wear out. What they do now is they bury in the road a coil of wire. Okay? Coil of wire buried in the road. Now, through that coil of wire is a magnetic field of the Earth. And part of that field is in that Earth, all right? Now, if you could change the magnetic field intensity of the Earth through that big coil of wire, what would you induce in that coil? Begin with a V. A voltage, isn't that right? So when your metal car drives, when your iron car, a wooden car won't work. When your iron car goes over that coil of wire, does it not alter a little bit the magnetic field intensity in that loop? Answer begin with a Y. And when it does that, it makes a little tiny electric current which activates the switch of changes the lights. Isn't that neat? So the next time you're driving near traffic lights, look down to see if someone hasn't putting down there a couple of coils of wire. Of course, you get two to make sure, huh? Check that out. Another thing, too, tape recorders. Tape recorders. What does a tape recorder do? Well, in a tape recorder, when you speak into a microphone, you get a little plug like Ted had to go back, forth, back, forth, and makes a little vibrating current in wire, right? What if that is passed down to a little electromagnet, and you drag by that electromagnet some rusty tape, and the rust is iron oxide. When that iron oxide slides by that magnet there, varying strength, you get on that tape then varying strength of magnetism. Some is magnetized a lot, some magnetized a little bit. And the little vibrations you're getting on the tape. Now you take that tape and bring it to another machine, I won't tell you the same machine, and drag that tape at the same speed past an empty coil of wire. What's going to happen to the magnetic field intensity in an empty coil of wire when that tape drags by? It's going to change. Isn't that right? And if a piece of tape comes by that's heavily magnetized, boom, you're going to get a big pulse of current. A little tiny bit, well, you can get variations. And isn't it amazing that that tape driving by there, the empty coil, the variations in the magnetism set up variations of voltage in that wire, Faraday's law, which then goes into driving a speaker, again, the plug going back and forth, glued to a what? A paper cone. And the paper cone vibrates the same way, and boom, you get music. So look, next time you look at your tape recorder, honey, what's underlying all of that? It's EMI. What are we talking about? Electromagnetic induction. Ain't that neat? Now I got one question to leave you with. I got two questions. Number one was, how did this thing, boom, fly off? What's the basis of that electromagnetic levitation? And the other question is when I crank this generator, it's harder to turn when it's lit up and easier to turn when it's not. Right now I'm turning only against friction. But when I hook it in and it becomes part of the circuit, it really is more difficult to turn. HC. How come? Think about that. It's physics, all right? Yay.